Good afternoon and welcome to Hot Code is Faster Code, JVM warm-up with Mark Price. Just a brief note about eSynergy before the presentation. eSynergy specializes in open source and cloud resourcing. If you are looking for a new opportunity or to build out your team, please get in touch after the webinar. Now, moving on to some housekeeping, if you have any questions for Mark, please fire them over via the questions box throughout, and Mark will answer them at the end of his talk. We are recording the session, and the slides and recording will be made available and sent to you tomorrow by email, along with my contact details. Now, I'm going to pass over to Mark to begin the talk.
Good afternoon, everyone. Thanks for joining me. My name is Mark Price. I'm a lead performance engineer at Elmex Exchange. At Elmex, we've built and operate a low latency trading venue. And for us, low latency means an average response time of about 80 microseconds through our system, and that includes 6 network hops and transit through 4 JVM. So I'm here to talk to you today about the JVM warm-up problem. This was the initial title for the talk, and I was kind of thinking about what we really mean by the warm-up problem, and it describes the effect of Java being an interpreted language and the fact that our programs don't always operate as quickly as they could when they initially launch, and that they take some time to reach a fully optimized state in order to execute with the highest performance. But this is a problem that's kind of common to all interpreted runtimes. So the JVM has a really nice way of sidestepping that problem, or dealing with that problem, I should say. And it's actually a really powerful tool. So instead of talking about the JVM warm-up problem, I turned it powerful technology that we get to use in our runtime. So a brief and probably unnecessary history lesson to start with. The reason we kind of have this the system in the first place, it's sometimes easy to forget, I think, with our good practices of continuous integration and continuous deployment, that way back when Java was kind of designed to write once and run anywhere, and this was at the time to address these different
I'm really sorry, but we cannot see your screen. Are you please able to share your screen?
Any better?
No.
You haven't set to share my screen, Adele.
You should go in now.
Sorry, everyone. I still don't see the dialog inviting me to share my screen.
Sorry, we are just trying to fix this. We are having few problems. Apologize about this. Hi, Mark. Have you got a request now?
No, there's no request for me to share my screen.
possible to log off and log back in, please? Sorry about that.
Okay.
Thanks. Hi everyone, thank you for your patience. We're just having a couple of technical difficulties and we should resolve it within the next couple of minutes. Sorry about this.
Hello, Mark. We can now see your screen. We can see it now, Mark. So you can start when you are ready.
Thank you. Okay, so I think I'd got as far as introducing myself and talking about the company I work for. I was saying that the reason we have the warm-up feature of Java is down to the fact that we are running an interpreted language. And that was a kind of a hangover from the days when Java was supposed to run on many different operating systems and many different platforms. And the design of the language was such that the bytecode was used as the intermediate representation of the actual program, and the vendors of the JVM would then target specific operating systems and hardware platforms. And I was saying that we kind of, these days we tend to, or certainly my organisation, we deploy to the same hardware and the same OS all the time, but you kind of forget that you should in theory be able to go and run your software on different operating systems and hardware. So I'm just going to take a quick look at what the JVM actually runs. This should be familiar to anyone who's a Java programmer. So we start off with some source code, and when we run the Java tool, it pulls in class path resources, and what's emitted by the compiler is bytecode. And this is the intermediate representation, which is interpreted by all JVMs. So the first part of the JVM that we're going to have a quick look at is the interpreter. So for an example, simple piece of source code, this is just a single function that performs a loop and adds together the integers 1 to 9 and returns the result. We can take a quick look at what that looks like in bytecodes. So to do this, we can use one of the JDK tools called JavaP, which is used for decompiling compiled sources. So we would call JavaP, and the -p flag would ask it to show us private members, so as much information as we can get out. -c requests that the code be disassembled into bytecode, and we give it the class path and then the class name that we wish to decompile. The output of that will be sent to stdout, and we'll see something like this. This is the bytecode representation of the method that I showed a couple of slides earlier. If you really like to understand what all these references mean, there's a link to Wikipedia there where there's the reference for all the bytecode instructions. But just walking through this code will kind of show us how the compiler converts from our source code to this bytecode. So starting off at bytecode 0, these are kind of executed sequentially by the interpreter. We load the value of 0 onto the stack, and then we store the top of the stack into stack slot 0, and this happens to be the sum variable. Then we load 0 again onto the top of the stack and store this into the first stack slot, which is the I variable. And bytecode 4, the iload1, this is the start of the loop form. So we load the stack slot 1 onto the stack, and that's I. Then we push 10 onto the stack. Then we compare the two values. If they're greater than or equal to 10, we'll jump to bytecode 20. So that's the kind of the exit of the for loop. If we don't jump out of the for loop, then we load sum and we load 1. We add the values together, and then we store the result back into the sum variable. Then finally we increment our loop counter by 1, that's bytecode 14, and then we have a goto which takes us back to bytecode 4, which is the top of the for loop. And we can see that eventually we'll load enough times to I so that we'll break out of our for loop, and then we'll jump to bytecode 20, which says I want to load the value of the 0th stack slot back onto the stack and then return that value. So that's the bytecode representation of that very simple for loop. So we go from something like 4 lines of code to 21 or 22 bytecodes because they're 0 based. So that's what the compiler is doing when it converts your program. So I'll talk a little bit about interpreted mode. Each bytecode is interpreted and executed at runtime, so that program will be executed by the interpreter sequentially. This is the startup behavior for almost all JVMs. If we wanted to mess about with this and kind of see how interpreted mode operates, we could force interpreted mode with a certain flag, that's xint. Normally we wouldn't want to do this because it causes the performance to degrade so much, but it's useful to just inspect the operation of the machine. And with this flag enabled, no compiler optimization is performed at all. So we're going to have a look at an example of that loop method that we saw before. And this is an excerpt from a JMH benchmark which I wrote for this talk. If you're not familiar with JMH, it's kind of the state of the art in benchmarking Java code. It's well worth a look, and it does lots of nice things like getting rid of dead code elimination and making sure that your benchmarks are actually measuring the right thing. So the benchmark annotation tells the JMH framework that I want to call that function many times and time how long it takes to actually perform the operation. So I have a number of test methods. The first one calls the doLoop10 method, which is the method we saw earlier. The next one calls doLoop100, which is a very similar method, but it's counting up to 100, and so on, doLoop1000, doLoop110,000. So running the benchmark gives us some fairly intuitive results. I've put them on a chart here. Both x and y-axis are log scale. And what we can see is that when running in fully interpreted mode, if we do 10 times the amount of work, then the operation takes about 10 times as long. And this is kind of in line with expectations. Instead of counting to 10, if we have to iterate up to 100, then it should take about 10 times as long. So when you're just locked in interpreted mode, you would expect that kind of behavior. However, that's not how modern JVMs are meant to operate. What we really want is the runtime to be able to optimize our code and make it perform a little quicker than executing bytecodes. Which brings us to the next part of the machine, which is the compiler. You'll probably have heard of the term JIT, so this is the name of the hotspot compiler. It stands for just in time. I kind of prefer to think of it as the deferred compiler, because if it's just in time, we'd like it to compile our code before it's needed, but actually it's always a little bit after you really want it to be compiled. This was added a long time back in the days of JDK 1.3 to address perceived performance problems with the JVM interpreter. And its mode of operation is to replace interpreted code with optimized machine code at runtime. So it works by compiling in the background, so obviously we wouldn't want it to store our application threads and do the compilation on the same thread that you were trying to actually perform your business functions on. So the compilation is done in the background and will get switched out once the compilation has completed, because it could be quite a long-running task. The interpreter works by monitoring the code which is executing using counters placed at preset points in the code. These are method entry points and loop back edges. So at the point where we jump back up to the top of the loop, and branches, so ifs. And all these places are instrumented to give the interpreter an idea of how frequently certain things are being executed. So if we look back to our previous method that we've been working with, the interpreter, when it's executing this code, will be keeping a counter every time the do loop 10 method is called, and also at the back edge of that for loop. So every time we go around that for loop, counter there would also be incremented. And these are the counters which are used to determine what code should be compiled to optimize machine code. There are two flavors of compiler in stock JVM. We have the C1 client compiler, and this can be enabled with the client flag, and we have the server compiler, which has the server flag. The client compiler is focused more on desktop and graphical user interface applications. So this is where you humans will be using the software, and you kind of want them to have an accelerated experience as quickly as possible, where you don't know that they're going to be using the application for a particularly long time. That was its initial intention. And this kind of goes back to the applet-based feature that was foreseen at the time. The server compiler is aimed at long-running processes and is more tuned for maximum performance. And this means that the server flag using the C2 compiler should produce the most optimized code. It may take longer to get to the point where it is optimized. The point is that it's able to make better speculative optimization, so it will spend longer monitoring and looking at your code in order to understand what are the hotspots and what should be compiled. In general, we wouldn't really choose client over server, but there's a slight gotcha on the 64-bit JDK. Client is ignored these days, so you have to do some fiddling to force its usage, which we'll see a little bit later. And a few years ago, there was a mode of operation enabled called tiered compilation, which is now the default. And this works by running the interpreter first will send compile tasks to the client compiler for quick responses, and then as time goes on and the counters increase, it will send jobs to the server compiler. And the idea with this is that you get a little bit of optimization very quickly from the C1 compiler, and then as your application executes for longer, you get improved optimization from the server compiler. So yeah, that's been the default for a while now, but we'll see its operation a little bit later. Now I'd like to just use a short animation to kind of show how all these bits tie together. When we start executing our Java program, it will generally be running in the bytecode interpreter, and so we have our program thread, which is doing our loop. And as this is executing, we can see that in the interpreted code we have the method entry point counter, and the interpreter is updating that every time it executes that function, and we can see that it's getting to a certain point, and then when it hits a threshold, in this case 10,000 invocations, the interpreter will send a compile task to the JIT compiler. This is the back end of the hotspot JVM, and this is where the background compiler threads will start to operate. So they will know which method they're they've been asked to optimize. The JIT compiler will generate some code which has the same effect, I guess, as the bytecodes which are being interpreted. And so it will look exactly the same and will have the same effects, but it will be highly optimized for the particular architecture that it's running on. And to note here, the loop counters, entry counters, will still be part of that optimized machine code because the compiler wants to continue working with the optimized code as well. Once that compile task is complete, there's something called the ITC adapter, which is the interpreted to compiled adapter, and that's a way that the interpreter has of jumping out to the optimized machine code once the compilation is complete. Oh yes, and once that's happened, the bytecode interpreter no longer runs the interpreted code, and execution just goes straight to the optimized machine code. So we want to take a little bit of a closer look at what's happening. That was a broad overview. If we want to see what the just-in-time compiler is doing under the hood, we can follow these simple steps. Unlock diagnostic JVM options tells the JVM that you want to start looking at internals. We can turn on log compilation, which will give us a lot of information about what the compiler is doing. You can run your program. A file will be generated called hotspot.pid with the process ID of your program. And then, unfortunately, this will probably be your reaction because the content of the file will look something like this, which I'm sure you'll agree is not particularly digestible. However, we shall dive in and have a look at a small example. So we're going to walk through how tiered compilation works on our particular code example. So I ran this program with those flags, and then I had a look in the output for the do-loop10 method. And what we can see is that we get a compile ID, which is the task going to the compiler. We can see the loop back edge count here, so this is the thing that will have tripped over the threshold and said that it needs to be compiled. And there's also the invocation count, so either one of those could have tripped it over. And we can see that the compile task is the C1 compiler, so this is a tiered operation here. We start off with the C1 compiler once we go over the threshold. If I look a little bit further down in that log file, I can see another compile ID, and this one's kicked out only a few milliseconds later. And we can see this time that the compiler is the C2 compiler. So at this point, our invocation count has shown the interpreter that this method is going to be called frequently enough that it's worth optimizing more and sending to the C2 compiler. Now, then we get to a further bit where we see another kind of compilation, and this is an OSR compilation. And this stands for on-stack replacement. And this is the JVM's method of replacing a loop body with an optimized implementation. So if we look a little bit further down, we can see that the bytecode index of the on-stack replacement is bytecode 4. And if you can cast your mind back to the bytecode of our method that we saw earlier, 4 was the index of the top of the loop body. So this is actually allowing us to hot swap in the compiled code even though we're still executing a loop. So there's our bytecode 4, which was the top of the loop, and we can see at bytecode 17 that's where we go back up to the loop. So the compiler is able to slot in a kind of a jump point there. So when we get to the end of the for loop, we go to 4, and then we'll be able to be replaced into our optimized code without having to exit the loop body. And this makes sense for long-running loops. You want to be able to use your compiled code as quickly as possible. So our method execution starts in interpreted mode. After our back edge count or the invocation count goes over the C1 threshold, we get C1 compiled. C2 compilation happens after we go over the C2 threshold, and then OSR starts executing the compiled code before the loop body even terminates. So that gets us to kind of the maximum performance as fast as it can. So if we want to have a look at a chart again and for what kind of speed up we get, and there's four tests here. One is the interpreted mode, which was the blue line, then we've got the C1 compiler, the C2 compiler. I had to use a 32-bit JDK in order to use the C1 compiler. So when I was doing it for completeness, I put the 64-bit JDK on as well, and that's the yellow line. So across the board, we always get a 20% speed up, but this is a really simple and daft test, so we would expect that speed up factor to be much greater for complex method and hierarchies, so we'd typically be looking at about 1,000 times increase. So that's how the compiler works and the kind of speed ups we can expect from it. Now, its mode of operation is that it makes speculative optimizations based on the observations it's made. But those observations could be invalidated at any time. So the compiler needs a mechanism, or the JVM needs a mechanism, to detect whether those speculations are still correct or if they've been invalidated, and to act accordingly. And the mechanism used for this are called uncommon traps. So these are injected by the compiler into the native code, and their job is to detect whether assumptions have been invalidated, and these are the assumptions that allow the optimized code to be executed. When an uncommon trap is triggered, then execution mode has to bail out to the interpreter, and this is kind of serious because you're now back in unoptimized interpreted mode, and we know that that is orders of magnitude slower than the optimized case. This is referred to as a de-optimization usually, so that's something to watch out for. And once we're back in interpreter land, then the compilation cycle starts again. So we'd have to go through the same process of warming things up. In order to see this in action, we're going to look at an example of something called type profiles, which is an optimization technique available to Hotspot. When we have a virtual method invocation of an interface method, the compiler will try and be clever, and if it can observe that only one implementation of that interface exists, then the virtual call can be optimized by inlining to the actual implementation target. And this gets us a performance win because you've got fewer levels of indirection, which is all well and good, but there is of course an explicit implicit assumption in this. And of course that is that if there is not only one implementation, then we could be sending the execution to the wrong target. So in order to demonstrate this, we've got this very simple interface calculator which takes an int and returns an int. So to demonstrate it, I have a very small test harness. We have a static volatile calculator, which is the first calculator implementation. And in this loop, I just iterate over a loop 1,000,000 times, accumulating the result of calculate result, and every 1,000 iterations logging out how long it took to do those 1,000 iterations. So here's our first instance. Here we are calculating the result and accumulating. Now, in order to trigger the type profiling behavior or the uncommon trap, in another you kind of get around the compiler's model of all the classes that have been loaded, and this will invalidate the previous assumption that there is only one implementation of calculator. So this load here should trigger the uncommon trap. When running this program, we can see that it takes us something along the lines of 60 or 70 micros to iterate through a loop 1,000 times. And if running with the trace class loading flag enabled, we can see, or we ask the class loader to log when it's loading particular classes. So we can see after we get past 500,000 or so iterations, we load the second calculator, and then our performance takes a dive, and it's about 6 or 7 times slower. And then after a little while, after we've been in interpreted mode again, we can see that the code gets re-optimized for the new implementation. And we get back to about 70 micros. Excuse me. So we can see the effect here of bailing back out to interpreted mode and then getting into compiled mode again. Just looking at this on a log scale graph, just to kind of show us what this would look like in real terms, we have some initial warm-up effect and then very quickly get to a nice stable time taken to complete 1,000 iterations, and then we can see clearly where we loaded the new class. The uncommon trap was triggered, we bailed out to interpreted mode where things started taking longer, and then got pretty quickly back to fast execution again, but that still took hundreds of thousands of executions of that method, and you have to kind of think that this is an artificial benchmark. It took very long, a very short real time to get back to it, but in a real app to execute something 100,000 times in order for it to be recompiled. Going back to our compiler logs, we can see here the node which represents that specific bit of inlining, and what it's saying is that for the receiver type 822, which is the first calculator instance, it's saying it's seen that 22,000 odd times, so it will place an uncommon trap for a class check and then inline the method call. And then further down the file we can see that the uncommon trap was triggered and for compile ID 9, and that means that we go back out into interpreted mode. So that's kind of what to look for in your log files if you want to see de-optimizations happening. So after a quick overview of an example there, I'm going to talk a little bit about strategies we can use to address this effect of the JVM. So first of all, what's wrong with the cold code? Interpreted code will take a little bit of time to be compiled. The compilation itself is fast, but our methods may not be hot for some time, because if they're not being executed enough, then the interpreter won't decide to compile them. Our compiled code is kind of ephemeral, so it will be cleared after a JVM restart or if you release your code, which is kind of unfortunate if your profile hasn't changed much. So for example, for us where this is important, market open in finance applications, if we do a code release over the weekend, then when market's open on Sunday night, our code we want to be pre-warmed, as it were, or something like an auction site where you kind of want everyone's experience to be the same. It's kind of unfair if someone's hitting an application set which hasn't warmed up. So the first approach we can take I call warm-up in place. So this is post-release or restart in your production environment. We want to send traffic through the system in order to exercise the code paths we care about. Obviously, it needs to match production-like traffic. We can't send in fake or stale data because it will exercise different code paths and we won't get the effect we want. It needs to make sure that it exercises all the code paths that we really care about the latency of. And it requires good data isolation because you do have to send in data that looks real and requests that look real. Ideally, you want to be just isolating that kind of almost by sharding rather than doing any kind of logic flip on whether this is something to actually process or not, because then you're just going to give the compiler false information. It's an approach that requires a lot of investment. So the way to approach it, first off, we need to understand what's happening. So first we need to observe, and this is running your systems and look at what's being generated by the logs. We want to understand how the compiler is treating our code, so what our count thresholds are for compilation or the size thresholds for whether certain methods will be too large to compile. Modify the compiler flags as necessary, now that you understand exactly how it's operating, given your code base, and then go back to the start. And this is something that we need to just kind of keep iterating on until you get the effect you want. So to make sure that your really hot methods are being inlined and that you're not having if branches which are too unstable, which will stop the compiler from optimizing it properly. Then we need to just tweak the traffic generator until it hits all the code paths that we care about. And this is an ongoing process that you kind of have to keep up with normal development as your application changes. The second strategy, ahead of time compile. This is, at the moment, I believe there are only commercial solutions. And with these solutions, they will, they are a JVM, but they will compile your bytecode into native machine code. So they kind of have they compile the entire runtime in. There are no warm-up effects with these solutions, which is one of the benefits. So for something like Market Open, you get native performance straight away. But they don't have the sort of ongoing profile-guided optimization that a normal JVM does. You can have static profile-guided optimization. So this is something more akin to C-type languages where you run a program with instrumentation within it to produce a profile, and then you feed that back into the compiler in order for it to make decisions about how to optimize the code. I haven't used these to see exactly kind of how that process works, but it will be something close to that. There's one other solution which kind of takes a slightly different approach. That's Zing JVM, the Ready Now feature. This again is another commercial solution. The way this works is by logging the compiler's operations to a file, so it kind of journals what it's doing, what its observations are. And then on startup, if that log file exists, then it will aggressively compile Java code as it's loaded to be optimized. This is really good because it reduces the warm-up time. It has the disadvantage that it's susceptible to large code refactorings. Obviously, if you kind of rename a whole load of methods or shuffle code around, then the profile isn't going to be valid. You can kind of get around this by shipping the compiler profile from your perf test environment along with the deployable to production. So that's another thing that could be worth trying. So there are a few tools that we can use in order to try and be able to understand a bit more of what's going on. The first one I'll talk about is JWatch, which has been around for a few years, and this is one person's effort to try and understand what was actually in the compiler log files, because it's pretty verbose. And it's quite nice. It will give you, you feed it the log file, and it will show you kind of whether your code is being compiled correctly, and it will try and give you some warnings about things if the compiler isn't able to do what it wants. So for an example here, it's telling me that my method will not be inlined initially because its number of bytecodes is too large. And this comes from this log message we can see at the front. A 55 byte method is too large to be inlined. It will also show you deopts, which are quite interesting, and it will give you some suggestions to try and work around those, which may or may not kind of match what you really need to do, but though it will look for de-optimizations in the code base and at least tell you about it. So in this case we can see that I had a branch which was taken most of the time, and then when it flipped to execute the false branch, then we got a de-optimization. So that's just another optimization that the compiler is doing under the hood. So that's good for an overview. If you really want to get a bit deeper into what's happening, we can use the assembly profiler from JMH. So this is for deep inspection of your code. You can only run it within the context of a JMH benchmark, so it's kind of, you can't deploy it with your system. It uses Linux perf events, I think as a Windows equivalent now, to sample the thread stack under the hood, but it's kind of outside of the JVM, so it's not susceptible to safe point bias. It captures the output of print assembly, and it matches up the assembly code with your Java methods. The one gotcha with this is that the assembly is architecture specific, so if you are doing this kind of profiling, you need to do it on the same hardware as your production systems. So I'm going to use that assembly profiler just to have a look into something that was a bit odd about that chart that I showed you earlier. You can see that the 64-bit C2 compiler seems to perform much better than the 32-bit C2 compiler. So on the y-axis is time taken to do the number of operations, and what we can see is that for C2 on the 64-bit JDK it seems to take just as long to do 10 operations as it does to do 100 operations. And this kind of puzzled me, so I thought I'd crack out this tool to go and have a look at why that was. So running the benchmark under JMH, it will give you the kind of a sample of the hottest methods as observed by perf. And what we've actually got here is it's only spent 10% of its time on the do loop 100 method, which seems a little bit odd. Actually, we've got a load more in the benchmark infrastructure, and we've got the calling method, which is all taking more time than the thing which should be doing a loop of 100. It will also print out for you the assembler of those methods, and what we can see here is that the do loop 100 method doesn't seem to have any looping in it whatsoever. It just has a move and an add and a pop. Now, if we were to sum up 0 to 99, we'd find that it was 4,950, and if we convert that to hex, we can see that it's the same value that we're moving into the EAX register there. And so what's actually happened here is that the compiler has seen that this is a for loop from 0 to 100, seen what it's doing, and decided to just fold that into a constant. So in fact we're not doing a loop at all, which is awesome. Compare this with when the loop count is 1000, and what we can see is that the hottest method under test, the hottest method is the method under test. So this is much more what we expect, that we spent 94% of the time in the loop method. And if we compare the assembly for the do loop 1000 method, what we can see is that it looks much more like a loop. So we have a bunch of adds, and we have some comparing, and we have some jumps. And this looks, a little bit more like the bytecode we saw earlier. Just to note here, there is one other nice little optimization that the compiler is doing for us. Instead of adding 1 each time around the loop, here it's adding a number of operations each time, so it cuts down the number of times it actually has to go over a loop. So going back to our chart, the difference here is that n was not 100 at this point. N was actually 1, because the method, once compiled to assembly, was just returning a constant. That's quite a surprising find. Okay, that's been a whistle-stop tour through some tooling. I would encourage anyone to go and try those out for themselves. It's well worth getting familiar with those tools. So I'm going to finish off just with a kind of best practices for how to interact with the JVM compiler. First off, it really likes small methods, and there are quite a few thresholds in there which are to do with bytecode and sizes or lengths of methods. So the compiler won't aggressively inline methods that are too big. So along with good design principles pointing us towards kind of small methods that only do one thing, they're really good for the compiler as well, and so they'll be executed or more aggressively compiled. Where we have megamorphic call sites, and this is means that when we have many different implementations of a particular interface loaded and available, even if they're megamorphic, the compiler will try to optimize them if they're biased towards a particular implementation. So if you call your first calculator implementation 90% of the time, or some threshold, that will be aggressively inlined, and you won't trigger an uncommon trap. In that case, you'll just take a different branch. If you're going to try and change the behavior or optimize the behavior of the compiler, you really need to use controlled tests. So these need to be repeatable, and you need to be able to observe what's happening and kind of understand how any changes you're making to the runtime flags are going to affect the program. This isn't something to just do in an ad hoc way and hope for the best. You definitely need to be able to measure the results to see whether they're having the effect you want, because it's entirely possible to make things a lot worse. We want to look out for failure to inline, so something like JITwatch will tell you this, or you can look out for that in the log files with Corley too large. Inlining is the biggest, or kind of the best optimization that the compiler has, because it allows it to then aggressively compile more stuff as it has larger code blocks to work with. We want to look out for de-optimizations. This is an indication that your code paths aren't as predictable as possible, or something is happening which is causing you to bail back out to an interpreter mode, which we kind of want to avoid. And we always want to understand what the compiler is doing before attempting to optimization. So this kind of goes hand in hand with controlled tests. We don't want to just kind of change flags and drop thresholds and hope for the best, because ideally you kind of want to target a low latency path that you want to be highly optimized, and work with the compiler to make sure that it has the information it needs. And this is really just kind of one level of the stack if you care about low latency and high performance. Underneath the JVM there's a whole operating system which is also responsible for slowing things down if allowed to do as it pleases. So this is only one part of the process of making everything as fast as possible. Okay, I hope that's been interesting and informative to everyone. I have a couple of questions which I'll answer. First question is, when warming up in place, how do you switch from warming up mode and turn the flag off? So I think this is a question about when we're running in production and we're running our traffic generator in order to exercise the relevant code paths. There's a kind of naive approach where you basically have your code ignore all the inputs, or at a certain point maybe just not publish out responses. This is kind of a bad pattern, because it means that you will, at some point after you've done your warm-up, you want to switch the flag on and say, okay, we're now accepting production traffic. But that could cause a bunch of de-optimizations, because you're going to be taking different code paths. I alluded to it earlier, but the best approach here is to do data isolation. So the way we do this is to have a kind of a data separation. So we are executing all the same code, but instructions that go in sort of come to an internal sync, and no customers ever see the results of those. And that allows us to send real traffic through our system, so we know we're exercising it correctly. It's difficult to get there, but it's well worth having. And there's another question. Would you consider using native code for performance critical functions? So I guess this is something like if we had something that needs to execute really quickly, would we want to use JNI and execute some C code? That would get you away from the warm-up issue, but I think it kind of depends on what the compiler is doing. I suppose we might want to do that if we could identify that the assembler that was generated wasn't optimal, and that we could do better ourselves. There it might kind of be worth it, but it would be something to test and make sure that it was actually going to be faster, because the JVM is very, very good at aggressively optimizing your code. So it would be a case of testing it to make sure that the win was really worth it, because you'd also have the overhead of going over JNI. Okay, if there are no other questions, I guess I will call it there. So thank you very much for joining me. I have one more slide at the end here. We do write a little bit about what we do at LMAX on our staff blogs. There's another link. That second one is a link to my blog, where I kind of did a bit of an analysis of the various flags that you can supply to the compiler. So in order to get certain effects like more aggressive inlining or more aggressive compilation, there are certain dials you can turn. So there's a reference there. I tweet on Twitter with that handle, usually about work and performance stuff, so say hello if you'd like to talk about this some more. And LMAX Exchange, we're always kind of interested in hearing from private developers, so if you're interested in working on a system where this kind of thing matters, then drop us a line on that email. Okay, thanks very much for joining me.